This is the last scenario. Okay? Let's read the problem first so that you have an idea of what this is about. It's a different way of preparing a buffer. You are tasked to prepare a 250 ml, 0.50 molar sodium citrate buffer with pH 7. Citric acid is a triprotic acid with pKa values of 3.1, 4.7, and 6.4. Unfortunately, only citric acid and 5 molar sodium hydroxide is available in the stockroom. Will you still be able to prepare your sodium citrate buffer using these two reagents? And the answer is yes. But before we proceed to that, let us discuss first about our citrate buffer. So this is one of, actually it's less commonly used, but it's also used in biochemistry. Because if you notice, its third dissociation has a pKa of 6.4, and this is close to the physiological pH. So citrate buffer can be used in biochemical experiments. So citric acid, so it's mentioned here, it's a triprotic acid. So its chemical formula is C6H8O7. So since all of you are good in organic chemistry, let me draw the structure of citric acid. So you see that it has three carboxylic acid functional groups, and these are the three ionizable protons. Okay, so now let me write the dissociation reaction so that you will just see how citric acid dissociates. So we have the first dissociation plus hydronium ion. So the Ka for the first dissociation is equal to 7.4 times 10 raised to negative 4. And if you compute for the pKa, you will get a value of 3.1 or 3.13. For the second dissociation, so we have C6H607, O7, 2 minus, plus hydronium ion. And the Ka for this second dissociation is 1.7 times 10 raised to negative 5. And if you compute for the pKa for the second dissociation, this is equal to 4.76. And finally, for the third dissociation, so we have C6H5O7, 3 minus, plus hydronium ion. The Ka for this last dissociation reaction is 4.0 times 10 raised to negative 7, and the corresponding pKa value is 6.4. So again, since our target pH is 7, we will take the third dissociation reaction as our basis. But again, the available reagent is citric acid. So the one with 3 protons still intact. So how do we do this? Again, we are preparing a buffer. So we will use our Henderson-Hasselbalch equation. So let's write it again. So just write it. Don't get tired of writing your equations. It's a practice. Okay. Now, in the logarithmic term of our equation, we look at our basis. This third dissociation reaction, right? So our conjugate base is this one, citrate, C6H5O7 3 minus. And our weak acid component is C6H6O7 2 minus. Okay. Next, we have our target pH, which is 7.0. We have the pKa value, which is 6.4. Now, what we do here, okay, we represent this concentration of citrate as X and the concentration of C6H6O7 2 minus as Y. Now recall that the given concentration of a buffer is the total concentration of our components, which means that X plus Y is equal to 0.5 molar, right? So we can write, actually, we can represent X as 0.5 minus Y, yeah? So here in the numerator, we will write 0.5 minus Y over Y. Solving for Y, you will get a value of 0.10038, or we can just approximate this as 0.1 molar. This is the concentration of our C6H6O7 2 minus, the weak acid component. And it follows that X is equal to 0.4 molar. And this is the concentration of our conjugate base, which is citrate. Okay. Now, from this molarity, we need to determine the moles. So moles is the amount. It's not concentration because concentration is amount per volume. We need to know the amount of these two components. So, let me erase these equations because I need space for the subsequent computations. How do we get the moles? We need the concentration and the volume, right? So moles of let's go for C6H6O7, which is the weak acid component. So we have 0.1 molar or 0.1 mole per liter. Just multiply this with the volume of our buffer, the target volume, which is 0.250 liter. And you will get 0.025 mole. Then we get the mole of our conjugate base, citrate, so C6H5O7 3 minus. So we multiply 0.4 mole per liter times the final volume of our buffer, 250 ml or 0.250 liter. And this will give you 0.1 mole. Now, here is the tricky part. These two components will now come from our citric acid. How will that happen? We will use sodium hydroxide. Okay, we will use sodium hydroxide to extract protons via neutralization reaction from citric acid. Okay, so we start with the fully protonated form, and we use the strong base, sodium hydroxide, to extract the protons until we get this form of our molecule. So what we do first is, so we add these two, so that's 0.125 mole. Okay. Now, this means that these two, okay, or this 0.125 mole will come from citric acid, which means we need 0.125 mole of citric acid, or C6H8O7, the intact molecule. Now, 0.1 mole from this 0.125, okay, so a part of this will need 0.3 moles of OH minus. So where did this 0.3 come from? We multiplied 0.1 by 3 because every molecule of citric acid, for it to become this citrate, the one with the charge of -3, for every molecule of this, you need 3 OH ions, right? So if I need 0.1 mole of this, okay, it means that 0.1 mole of citric acid must be neutralized by 0.3 moles of hydroxide ions. And with the same line of reasoning, the remaining 0.025 mole of citric acid, this need 0.2. Is that 0.2? So we multiply 0.025 by 2. So we multiply this by 2 and we get 0.05 moles of hydroxide ions. So we only need to multiply it by 2. Why 2? Because for every molecule of citric acid, we only need to remove 2 protons. So you only need 2 OH minus ions. Okay? So now we know how many moles of hydroxide ions we need. With that, so we will add these two. So the total amount of hydroxide ions that we need is 0.35 mole of hydroxide ions. With this and with the given concentration of our sodium hydroxide solution, we can determine the volume that we need. So how many ml of the sodium hydroxide solution do we need? So we need 0.35 mole, and we divide this by the concentration, which is 5 molar or 5 mole per liter. And this will give you a value of 0.07 liter or 70 ml of 5 molar sodium hydroxide solution. And finally, so we know that we need this amount of citric acid. So we can determine the mass of citric acid. So we need 0.125 mole of citric acid. And to get the mass, we just use the given molar mass of citric acid, which is 192.12 grams per mole. And this will give you a value of 24.015 grams. So how do you prepare this? You simply you weigh your citric acid, the solid citric acid, you dissolve it in, let's say you dissolve it first in 150 ml of distilled water. So you have your solid citric acid, dissolve it. So after dissolving your solid citric acid, you add your 70 ml, 5 molar sodium hydroxide solution. You stir it again, check the pH. So if it is, if the pH is your target pH, 7.0, then you can just add water until the volume reaches 250 ml. If it's not equal to your target pH, again, you adjust it with hydrochloric acid or sodium hydroxide. After adjusting, that's the time that you add water so that the final volume is equal to 250 ml.